Okay, hey, thanks for joining me again. Sorry, I had kind of a perfect storm of computer problems, and then had a big meeting last week with external folks. I'm kind of back in the saddle now. Let's go through what's really the heart of material science, which is really this idea of microstructure. And along the way, we're also going to go through the idea of length scales, and really the one of the most interesting things to me anyway is how length scales come together in material science. So that's what we'll be talking about in this lecture. Please, as always, let me know if you have any comments, questions. Give me any idea if it's uh, too deep, too shallow, other things you'd like to see. And the other thing we'll also put in here is some links to some other good stuff. So what I hope you'll get out of this, and there will be a multiple choice quiz coming up soon, is what do we mean when we talk about a material microstructure? What are the key features of a microstructure? Um, I'm going to give a very cursory overview of how we examine microstructures, and there's a number of tools we use. Mostly what I'm going to do is show you what typical microstructures look like, and then we're also going to talk a fair bit about typical sizes and size scales and see how that all fits together. And I think there's really some deeper science that can go into this that really can be quite inspirational for how kids can see the world in doing that. So onward with this. So here are examples of microstructure. Um, the top two are the top two here are real micrographs. The bottom here are cartoons. This is something called an orientation image, and here these are what we call grains. We'll go through this a little more carefully. They're basically single crystals, and each of these single crystals abut up against one another. And you can see the orientations by the color, and basically we have a technique that figures out what the orientation of each little grain is, each crystal is, pixel by pixel, colors it that way, and we can see uh, what the relative orientations between these boundaries are, and I'll go through that a little bit more carefully later on. This other image is something we call a transmission electron micrograph. And what you see here, this is kind of this is the material that's in a turbine blade. In specific, this is a nickel-based superalloy. And you can see that these are basically chemically distinct from this. This is almost like a bricks and mortar structure. And then these black things that go over this, black things, these squiggly lines, are dislocations. And we'll talk a little bit about what these things are, but basically this is one phase. Down here, the mortar is equal to something called gamma, which is basically nickel-rich alloy. And then these bricks that you see like this, these are what are called gamma prime. And this is an ordered phase of Ni3. I'm going awfully fast and I'm throwing a lot of stuff out all at once, but that's Ni3Al. And so it looks sort of like this. This is the nickel-based alloy here. What we mean by an alloy is it's nickel with some other elements in it, and then you've got this ordered phase. That doesn't show up very well. And then you've got this ordered phase in here inside of that. And that basically makes obstacles so these defects called dislocations can't move through the structure. And in this course, we're not going to be able to go through this in any depth, but this structure that you get, these ordered regions with these more disordered regions around them, gives you remarkable strength. We can get very high strength out of these things, very much right up close to the melting point of the material. And you can see these boundaries are very orderly, and these boundaries between these crystals here, this is a schematic. Beneath in each of these cases are schematics. These boundaries are very much less orderly, and we'll get into all of that. This is just this point an introductory slide, and we'll go through what the features of microstructure are a little bit more. So with this, what I want to do is go through a little bit and remind you about powers of 10 in length scales. And so again, logarithmic scales go like 1, 100, 1, 10, 100, 1,000, etc. Each time going 10 times bigger, or you can go back and go 10 times smaller. And again, logarithmic thinking, in my way, is really a great way to see the world. It emphasizes the big trends that you often miss if you're just looking for the little changes. You have to look over large sweeps of time to look for things like global warming. And if you're just looking over, short length scales, and you're looking for something that persists over tens of thousands of years, if you look over a 1 or 10 year scale, you can't say much. Let's see, don't show the message again. So hoping this continues and keeps recording. What I want to do is show a YouTube video. There's a couple classics in here. Need the arrow. Click that. This is powers of 10 done by IBM some years ago.
Picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October.
So shows starting in a
human with a scene 1 meter wide,
length scale,
which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider.
And I'm just going to be kind of quiet.
This square is 10 meters wide
for a second. I'm not going to show the whole thing.
In 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Power boats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters, the distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move.
Now you're seeing orbits of planets.
That odd orbit belongs to Pluto, a fringe of a myriad comets.
Go a little further.
The Dipper.
Trying to get into galaxies.
Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy.
You're up here at very long length scales.
Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great
and of course what they do is they go back here, and now they go back the other way.
Mission turn. An outer layer of cells.
Fantastic
felty
voyage.
Collagen.
Back in.
The capillary containing red blood cells and a roughly lymphocyte.
And this is really what material science is
We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears.
Interact with one another.
The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter...
Let's stop there, go back. So that's, and there's some other nice versions of that. This one I think is absolutely fantastic and is good for this thinking, which in my mind is really an important part of material science, is being able to think over these diverse length scales and time scales. There's a little slicker version from the movie Cosmic Voyage with Morgan Freeman, and then these are kind of cheesy setups, but the Simpsons also did one of these as their couch gags, which is based on this and funnier, but kind of makes the same point, and I'll let you watch that on your own. But point is, this is a big deal for us in material science, is understanding where we're at with length scales. And I used this in the last lecture, and I kind of and with the IBM thing, it sort of starts primarily here at kind of the human scale and goes out, and I think they went out to about 10 to the 19th or 20th. We could also start this way and go this way to about 10 to the minus 15, and this gets you to a proton diameter. And if you watch the IBM thing to the end, they go a little bit, I think they stop at the protons. That's about as far as they could go in 1977. I think physics goes a little bit further. But this is sort of where we care in material science. Really, what we start to really care about is the atomic repeat distance in metals, polymers, and glasses. And that's about 0.25 nanometers is the international standard unit, or about 2.5 angstroms. And that's really about as short a length scale as material scientists tend to think about. And then we kind of stop thinking about things maybe, around a few times human height. It's still in here. We've got about 10 orders of magnitude, which is a mind-bending amount. It's if you just again, going from an atom to something really big, it's not even a speck of dust alongside the height of the Empire State Building. And what we contend is that all these length scales, there's really scientific action at all these length scales that we want to be able to capture and understand. So these are the ones that we care about. Really, down here, anything here beneath this is high energy or solid state physics. And the reason it's high energy physics is really we use things like colliders to try to break protons into smaller bits so we can see what's in them. And then and so this is an angstrom, and the SI units, go powers of 3. We go nanometers, is 10 to the minus 9 meters. A micrometer or micron is 10 to the minus 6 meters. A millimeter is 10 to the minus 3 meters. So a micron is to a millimeter is to a meter would be out here. So this would be a meter out here. So micron, millimeter, meter. And out here, this is really, kind of mechanical or civil engineering or architecture, other things goes out here. And these length scales are really the domain of material science. Really going from atom dimensions all the way up. And as I say, there's action at all of these levels, which is fascinating to us as material scientists and also somewhat frustrating, but we're the guardian sort of all of this, and you'll see that as we go through this. So again, kind of collecting the length scales here. Materials really are engineered microstructures. If we have something like an airplane, this is a military aircraft, we could do the same thing with a commercial aircraft. Back in here, we've got these engines. You look at these engines, and these engines go for thousands and thousands of dollars per pound, and they weigh hundreds and hundreds of pounds. They're very expensive, very highly engineered, and there's real action back here in the hot section. This is the most technically challenging part of the engine. You've got very, very hot gas. It's very close to, sometimes even above, the melting temperature of the nickel-based alloys that are going over this. We've got this thing which is called a turbine blade. That's put into that thing. So the turbine blade is tiny on the length scale of the airplane. And then these also have a ceramic coating on it. They also, you see cooling channels. There's a little bit of cool air that comes through here and comes out and helps cool the blade to keep it from melting. And then this is the structure that I talked to you before about, which is what we call a gamma prime structure. And it's these brick and mortar structures that keep defects from moving through the structure and keep it from bending. And you can see this is 1 micron here. So this distance is 1/1000th of a millimeter. And the human hair, for example, is about 50 microns. So you can see this is a lot of action going on in something much smaller than a human hair here. And this is what we care about. This further is made up of atoms and defects and so forth. There's a lot of action going on here, and that's what we care about. It's a lot like that IBM factors of 10. Each length scale you look at, you can see certain aspects, but other aspects become very difficult to see. So I'm going to try to keep this down here at the bottom and try to inform this figure to show where we're at in terms of length scales. And with this, we'll talk about certain features. Usually grains, we're talking about on the order of 10 microns to a millimeter. These are key vocabulary. Grains are really crystals. Phases, what we mean by phases are areas that are physically or chemically distinct. Chemically or physically distinct regions. For example, back here, this is a two-phase structure. This mortar is basically a disordered nickel alloy. These bricks are Ni3Al, an ordered compound, and because these are chemically different from each other, so they're distinct, we call this a two-phase structure, meaning we've got a gamma phase, which is a nickel-based, and a gamma prime phase, which is an ordered phase. A real simple way to see phases is if you've got a glass of ice water, you've got water in there, which is liquid, ice, which is solid. They're chemically the same thing, but they're also physically distinct. The ice is solid, the water is liquid, different physical properties and so forth. And if you've had chemistry or are a chemistry teacher, you're very familiar with this idea. Another thing is solutes. These basically are atoms that are different than the host within a crystal. And so the atoms we're talking about, again, these are about 2.5 angstroms or about 0.25 nanometers. So, kind of atoms and solutes. sit about here. Point defects are things like vacancies or interstitials. These would also sit at about the same place here. And line defects can be kind of skinny in one dimension, long in the other. So again, we're talking about something like 0.25 nanometers one way. That can be very long the other way. In this course, we will not talk very much about line defects at all. They're remarkably important. We talk about the mechanical properties of materials, but we won't really talk about them. Planar defects are, for example, things like grain boundaries we'll talk about. Again, they're going to fit in this part of the size spectrum. And then volume defects might be things, for example, like voids, which could be sort of almost anywhere along the spectrum, depending on how I don't know, what we're looking for. So again, just to go back to that example I've kind of hit a couple of times already, these nickel-based superalloys. Again, we have this gamma phase, which is just a nickel-rich alloy, which sits here. And then we've got these gamma primes, which are these bricks, which are an Ni3Al structure. And there's much more detail there than you'd really like, than we'd necessarily like. But there's a lot of research that's gone into these kinds of materials, and they're really important. The stronger you can make these materials at high temperature, the hotter you can run the engine. And if you can do that, you can run to much higher efficiencies. So there's huge amounts of money that are either saved or wasted, depending on how hot you can run this and how well these materials work. So let me go back and be a little less introductory and talk about the way real materials are made. If you take a piece of steel, ordinary steel, take almost any piece of steel off of a car, and if you could do an X-ray diffraction experiment, and if you've seen that, great. If not, don't worry about it, but you would find that the material is entirely crystalline. And what we mean by that is at any point the atoms are lined up in some sort of registry like this. In this case, this is a face center cubic crystal. This case over here is the body center cubic crystal. And these crystals are small. They're relatively small, and they're on the order, of probably 10 to 100 micrometers would be the size of these crystals, and they come together. This is a kind of a cartoon down here of what a polycrystalline solid might be. So this would be a single crystal. This would be a polycrystal. And by a polycrystal, what we mean is we've got all these single crystals that butt up against each other, and they come together and make this up. And this is a crystal, that's a separate one. Each one has a slightly different orientation. So for example, this is a prominent direction. This might have that prominent direction going this way, that might have it going that way, the other might have it going up and down somehow. And they're not, and each of them is fairly perfect, but they meet up at these boundaries, and these boundaries we call grain boundaries. The other thing that's interesting is these crystals, even for something that's cubic, have very directional properties. And this one is face center cubic, this is body center cubic. And what's very interesting is, for example, these crystals can be much stiffer along one direction than along another direction. And generally, a crystal will be stiffer along this close packed direction. And in this course, we won't have any time to really get into details of crystallography, but again, this is an interesting and vast topic that you could get into fairly deeply. Okay. So again, single crystals can have these very anisotropic properties, meaning that the properties are different depending on what direction you look at. Whereas if you have polycrystalline materials, generally those properties get averaged out so that the overall polycrystalline solid ends up being pretty isotropic, meaning the properties in this direction, that direction, or this direction are pretty much the same. And we can also take something that has a lot of single crystals, and we can sometimes make them textured by rolling or other processes, meaning we can get the crystals aligned in a particular direction. So again, with single versus polycrystals, usually the properties don't vary too much with direction. Sometimes they can, and that's something that we can use when we really want to improve properties. And again, this is something I don't want to go too deeply into. So this is the main thing I do want to talk about, is really looking at microstructures and giving you some idea what microstructures look like, because again, this is really the heart of material science, and I think you could make opportunities for students to look at microstructures and try to feel like they understand what goes on within a material, particularly in the context of a material science course. So the most common thing that we do is optical microscopy, and always the most difficult part of microscopy isn't looking at the sample, but it's usually preparing the sample so you can look at it. So optical microscopy, because of the wavelength of light, is about on the order of a couple microns, a couple thousand, a couple millionths of a meter. You don't get resolution beyond about 2000 magnification, meaning that there's a resolution limit of about 1 micron or so, is about as far as you can go, 1 times 10 to the minus 6 meters. So in order to perform this, what we end up doing is, first of all, we take whatever we're interested in, polish it very carefully, and at a place like Ohio State, we've got equipment where we can take a material, cut it, sand it, grind it, sand it, polish it, get it down so that you basically get all the scratches out. Then what you do is you take that surface and you put a little bit of acid on it. And when we put acid on a surface, we call that process etching. That changes the reflectance of the surface locally, depending on what the crystal orientation is. And then we can look at this with a microscope. And when we do that, we see things that look like this. And we know that basically each of these colors, again, sort of represents a different crystal orientation. So I can tell you what the grain size of this material is and so forth, and that's really the heart of what we'll do, and I'll show you some examples of that. So here's kind of a nice example. This is a cast, and I usually try to be pretty careful about where I take things off of the internet. This one I took from somewhere, I can't tell you exactly where. And this one was chemically etched so that the chemicals give you slightly different colors. And these, I can tell you, are dendrite cores. When you solidify metal from the melt, it tends to form these beautiful shapes and rejects solute out. There's more here than I can go into, but this is a standard solidification structure of an alloy. And when I say an alloy, what I mean is a mixture of elements, and that's what you end up seeing. So this is a little more complicated than what I want to show you, but I do want to show you another great site, and this is one out of Cambridge University. It stands for disseminate. I'll do it on the site, but promotion of material science through information technology means. And again, I'll change the arrow, and we'll click the site. And dissemination of IT for the promotion of material science. That's what this means. I no longer can write on this thing, but there's actually a lot of great stuff on this site. Now, as much as anything, wanted to take a couple minutes and just show the site off. but you can see there's modules on all sorts of great stuff in material science, and a huge amount of stuff. And this has all been quite well vetted, written by people at Cambridge University, and so it's high quality stuff. It's really above typical high school level, but again, I think the point of this course and and this site is to give you background beyond what you'd normally do with your high school. There's also some great videos in here. Apparently, I may not have, if I have the plug-in, but things on experimental procedures, industrial processing, for example. I can click on that, see what they have, the composite fabrication, and so forth. Really great stuff. I encourage you to look at this. Investment casting, for example, is a topic that there's a fair bit of interest in in this whole process and with the ASM camps. But mostly what I want to show today is this micrograph library. And there's a library here with micrographs, and I could put in AL for aluminum space and enter. And then here are, for example, the micrographs. Here's a nice example of a two-phase system. This is a solidification of a 67% by weight, 33% by weight copper aluminum structure. And these two phases, and again, all good material scientists always mark the scale. You see that there, it's 15 microns, 15 millionths of an inch. And one of these phases is aluminum, and the other phase, I believe, would be AL3CU, I believe, is about the composition. I could, if I could look at a phase diagram or remember the composition, look at a phase diagram, I could tell you. In this particular image, I can tell just by looking at it, is a scanning electron micrograph, one of the tools that we use. I'll talk a little bit about some of the tools in a moment. Let's continue to go back. A typical light micrograph might be this one, micrograph 1, 75% aluminum, 25% copper. Again, look more closely at it. This is a light micrograph, 40 micron marker, and then this is aluminum that's solidified first, and then this is a mixture of two phases, the light phase being aluminum, and then the darker phase being an aluminum copper compound. And that's what a typical microstructure looks like, and we material scientists, put these things together like this all the time. So let's so that's primarily what you do with light microscopy. This picture you have here is based on light microscopy, and that's what we do most commonly. Great technique, doesn't have, there's a lot we can't get out of that. There are other techniques we use. Electron microscopy is more expensive, takes more work to prepare the sample, need much more expensive equipment. But what you can get out of that is you can get imaging, you can get diffraction, understand the orientation of crystals. You can also, if you bounce electrons off of things, you can identify what they are chemically by looking at the X-ray signals that come off. And all of this can be done at ridiculously short length scales, right down to looking basically at individual atoms or columns of individual atoms, and I'll show you some examples of that. And basically you can't do justice to this in this course. But what I do want to do is as much as anything, one of the great things about science is, kind of looking at the zoo of what you can get, looking at, we all may not have degrees in astronomy, but we like oogling at the stars and the galaxies. And what I want to do with the rest of this is kind of go backwards and look a little bit about what things look like at really short length scales. So, and the other technique we often use, just before I get into that, is X-ray diffraction. In X-ray diffraction, we can tell you what the crystal types are, what the spacings between atoms are, what the orientations are, and also what the overall crystal perfection is. And again, way beyond what we're going to do here, but I just want to mention that for completeness. So again, these are sort of what the individual crystals are made up of. These are the single crystals that you put together to make up the polycrystals. These are examples of ionic crystals. This is an example of graphite, where you've got strong covalent bonding within the plane for those of you who are chemistry teachers, and fairly weak secondary bonding between the planes so they can slough off. But within these planes, you get very, very high strength, very, very high toughness. And in all of these cases, the atomic interatomic spacings are really in this range of a few angstroms to a few nanometers. That's always where we're talking about. The other thing I mentioned a little while ago is cast versus wrought structures. If we cast something, you probably watched ice crystals form on your windshield. Sometimes on a cold morning, you find that they form these branchy patterns. These are what we call dendrites. You can see the same thing on your car window in the morning. You get these also in solidification structures. And each of these dendrites, these little branchy things, again represent single crystals. And this is what we see with a cast. And when we mean cast just means we had molten metal alloy, molten mix of alloy, molten mix of elements to cool it down. We end up getting something like this, and this is copper nickel. Now we can take the same alloy or a different alloy, and we could take this and deform it and heat it up again and recrystallize it. And what you'll often see is something again that looks much more isotropic. You basically can break up those dendrites, and if you take a material and deform it by some process like rolling, for example, we've got big powered rollers like this. If something comes in like this and out the other end, this is what we'd call working the material, and the past tense of working, almost forgotten now, is wrought. And this is a wrought structure, meaning it's been deformed, and you've lost this kind of material, these gross dendrites and so forth. Generally, wrought materials have better properties than cast materials. That's why we almost always use wrought materials. Now this is kind of often we mix wrought and cast materials, and this is an example of a weld. And for example, what we often see is initial base material over here that's wrought. We see material in here that's cast. When we do welding, we melt the material. And then we also see an area in here called a heat affected zone. We often do that in shorthand, call it an HAZ, heat affected zone. So again, you can see kind of the size scales here. This is about 400 microns. This would be up in 1 micron, 10 microns, 100 microns, sort of in, this sort of range here is the micrograph size we're seeing. And then if you look at these weldments, again, you're out here, in the millimeter range. Again, the action I was showing you all back was back down here. So there's many, 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 many atoms that are making up these dendrites. And you can see also that this hints of different phases as well, going back to the vocabulary. You can see this is one kind of crystal, and in between there's this darker crystal that might be indeed a different phase. So again, going back to grains and grain boundaries, this is probably something like 40 microns, fairly fine-grained material. So again, we're dealing in a size scale about like that, a few microns on up. And these are all single crystals. and they've got to meet somewhere. So the grains come together, the areas they meet, sort of a planar defect. We call those areas they meet grain boundaries. We go further and can actually look and see what these grain boundaries look like. These interplanar spacings are on the order about 2.5 angstroms or 0.25 nanometers, and you can see how these planes come together and these meet with line defects in between them. Here you see they're coming together in a more disordered way, and at the atom level we see that these things have to come together, and there's some messiness that goes on here. And generally, grain boundaries help improve strength at low temperature, but at high temperature they actually degrade strength. They can cause some problems. So again, we're mixing features that are down here for the atom size with features that might be up here on the micron level for the grain size. So again, there's thousands and thousands of atoms that put these things together. And this is taken high resolution electron microscopy. Let me just show a couple brief but more complete studies that I just pulled out of the literature. This is some work out of Australia that again just shows high resolution electron microscopy. Again, you can see kind of the length scales. I think length scale, that wasn't the paper in the accompanying picture here. Maybe I cut it off or something. But this one, what you see is, if you look at aluminum alloys, the way we make these things strong is we put in these very fine particles, and these end up interacting with defects called dislocations. That's how we make them strong. Putting in these small second phase particles is really important to the strength of aluminum alloys, and this group did a study on how these really small phases nucleate, and you can see the size of these things that we care about are on the size scale of 100 nanometers. So if we look on here, this is 1 nanometer, 10 nanometers. This is about the size scale we're talking about. Again, grains are up around here, so they're much, much smaller than the grains, but again, much, much bigger than the atoms, but somehow they happen to come from the atoms. So these precipitates are really important. This group wanted to see how they are made. They looked at the atomic scale. They used high resolution electron microscopy. Basically, each dot here represents a column of atoms. They could identify that this is the stuff that this is basically silver precipitation within aluminum. They could see this on the atomic scale. Very cool sorts of things. And again, it just shows there's a lot of action that's going on at these almost unfathomably small length scales. And again, this distance between two of these planes is going to be on the order of about 2.5 angstroms or so. This comes from some work I was involved with a couple of years ago. And basically the question is, we know that for this particular alloy that's used in turbine engines, sometimes it's very crack resistant, sometimes it's not very crack resistant, and we could classify some alloys seem to have very high resistance to cracking in humid air, some had poor resistance to cracking, and depending on how you process this material, you could get a range of microstructures that you could see differently in light microscopy. You can see these, and again, these are all the 100 micron scale, so you're up around here. A tenth of a millimeter is the size scale you're looking at. If we pick one of these structures, and what you're seeing also is second phases that are coming into this. You're also seeing some other line defects called twins that come into this. But we can also go take these things, drill down, look at this with orientation imaging microscopy. We can understand where there are low angle and high angle boundaries. Then we could also take that and correlate that to cracks. And what we found is that some of these low angle boundaries or special boundaries like these twin boundaries are very resistant to cracking, but there are other boundaries that are very prone to cracking, and we could use these microstructural studies to understand which boundaries are prone to cracking and what kind of microstructural features give us crack resistance. And it turns out that by putting a lot of defects into the structure, it can sop up things like hydrogen or other bad actors, and that can minimize the propensity for this particular alloy to crack. And that's what we were really worried about. And again, we're working over a range of length scales with this, worrying about how atoms interact with these large crystals. So let me wrap this up. So hopefully with this you kind of got an idea of what we mean when we talk about microstructure, what the key features are, how we examine them. We can use optical microscopy, scanning electron microscopy, transmission electron microscopy. Again, I can't get even close to telling you how these procedures really work in detail. Showing you what some typical microstructures look like, how we kind of start to examine them, where you can find them. Told you a little bit about the typical sizes of the features, and those are really the goals. Hopefully you got that out of that. I will be posting a quiz very soon also to hopefully very shortly after this lecture's up, so you can see if you really understand this stuff, and that's required to get credit for this. And hopefully from this you also got the key vocabulary out of this: grains being crystals, phases being areas that are physically distinct from one another, solutes are just other elements tossed into the crystals, and then defects are really the things that give materials their properties. And these defects exist over all of these length scales, and that's what keeps things quite interesting. Please ask any questions if you have them. Again, I'll put a quiz up as well. Hope all's going well, and we'll talk soon. So again, I did put a conclusion slide, and that is microstructure is the heart of it all for we material scientists. So thanks for listening, and talk to you soon.